Hi everyone and welcome. In today's video, we're going to explore a deeper connection between signed area functions and general antiderivatives. The main question we will be exploring in this video is, can every antiderivative for some function f be written as a signed area function? And so let's begin to slowly dissect and understand what this problem statement is asking us. We begin by recalling one of the assertions of the fundamental theorem of calculus, which is that all continuous functions have antiderivatives. And moreover, the fundamental theorem of calculus even gives us a way of how to write down an antiderivative very quickly. So if you're given some function f, one way you can write down the antiderivative for this function is as a signed area function. So the fundamental theorem of calculus asserts that when you differentiate this signed area function with respect to x, with respect to the upper limit, then the derivative and the integral sort of cancel out and you just get back the integrand f of x. And so the question is, if I have a function f of x and I come across one of its antiderivatives, then is this antiderivative that I'm looking at just one of these signed area functions for maybe a particular choice of a? And the answer to that question is actually a no. So although there's no doubt that signed area functions are antiderivatives of the original function f, they are very particular and special antiderivatives that satisfy a geometric condition, which is that the signed area function evaluated at its lower limit or lower bound, it will always be 0. To see why that's the case, well, this is how the signed area function is defined. The variable is that upper limit. And so when you plug in that lower bound a, then you get the integral from a to a. And what's the signed area over this interval that has like 0 width? It's 0, right? So this is a property that we also discussed before. And so what this implies is that all signed area functions have at least one x-intercept. They will touch the x-axis at some point, at least once. However, general antiderivatives have no such requirement. They're not required to touch the x-axis at all. Here is a nice way to visualize and summarize our discussion above. Let's suppose you're working with some function, lowercase f, and this white circle encompasses its most general antiderivative. So every single antiderivative of my function f is somewhere in this white circle, okay? So the entire family of antiderivatives is represented by this white circle. Then the signed area functions are particular antiderivatives, and in general, usually, they form a subset of all my antiderivatives. These are the antiderivatives that have at least one x-intercept. But as you can see, there might be some other antiderivatives of my function that do not touch the x-axis, and those will be over here. Usually, the signed area functions do not exhaust all of the antiderivatives for some particular function f. Next, I would also like to take a look at an example to illustrate this idea further. Let's take as an example the function f of x equals x. Its general antiderivative can be found by using the power rule for integration, where you add 1 to the exponent and you divide by the new exponent. And so the most general antiderivative of this linear function is 1/2 x squared plus c. So what this means is that if you ever come across any antiderivative of this function f, then it's going to be one of these guys with maybe some constant value c. So it might be like c is equal to -17 or c is equal to like 3. But every single antiderivative of this linear function is one of these parabolas just shifted up and down. Okay? Now let's consider the signed area function, which is the definite integral from a to x of t dt. We can evaluate this definite integral just by using the fundamental theorem of calculus, but the evaluation part, where we need to find a particular antiderivative, in this case we used t squared over 2, and then we evaluate the antiderivative at the upper limit minus the output at the lower limit. And so now the question is, let's suppose that you come across some antiderivative for this function. Let's suppose that it's f of x equals 1/2 x squared minus 17, for example. Okay, so you come across this particular antiderivative in the wild. And the question we're asking is, can this particular antiderivative be expressed as a signed area function, as an integral, maybe for some choice of a? Is there a value of a that will yield that particular antiderivative? In other words, is there a way to reduce this constant down to -17? And so that is the question that we're asking. we will let C be an arbitrary but fixed constant, and we're asking, is it always possible to find a real number, that lower limit a, so that the signed area function, this integral, when you evaluate it, it will yield that particular antiderivative with that fixed C value. And so let's go ahead and try to solve this equation. We're going to plug in the expression for a of x, which is this guy over here, and then the expression for the particular antiderivative over here. Something nice happens. The x squared terms just cancel out, and you're left with this expression. Now we can just multiply both sides by -2 to get over here. And lastly, we can just take the square root of both sides to get over here, a in terms of c. And so the significance of this formula is that when someone chooses a particular value of c, this formula will help you find the corresponding value of a, so that the signed area function simplifies into that particular antiderivative that they picked. Next, let's take a look at when is this a value well defined. So if c is non-positive, meaning negative or 0, for example, take c to be -2, then when you sub -2 in here, the negative and the negative become a positive, right? When you multiply two negatives, you get a positive, and then you can square root the positive, no problem. And so in this case, real solutions exist for a. And so in that case, when someone picks, for example, the antiderivative 1/2 x squared minus 2, in that case, it is possible to solve for that lower limit and express this particular antiderivative as just a signed area function with that particular lower limit a. However, the issue comes when you pick a c value bigger than 0. Because if you pick, for example, c equals 1, then you have a negative number multiplied by a positive number, which gives the inside of this radical a negative result. And you cannot take the square root of a negative number, at least in the real number system. And so no real solutions exist for that lower bound in that integral. And so in that case, if you take like the antiderivative 1/2 x squared plus 1, this is an antiderivative that cannot be expressed as just a signed area function for some choice of a. There's no real value of a that will reduce the signed area function into that particular antiderivative. And why is this the case? It's because signed area functions satisfy a particular geometric constraint, which is that they need to have at least one x-intercept. But if you take a look at this antiderivative when c is positive, so let's take c to be 1, in that case, this is just a parabola that is shifted up. And so this parabola will never touch the x-axis. It will never have any x-intercepts. And so this is an antiderivative, but it is not a signed area function because it never touches the x-axis. It never satisfies that geometric constraint that signed area functions are supposed to have. So now you might have some more questions about what type of antiderivative do we have when c is positive. Well, when c is positive, we still have an antiderivative. For example, 1/2 x squared plus 1. This is still an antiderivative of f of x equals x. Okay, so there's no doubt about that. If you differentiate this, you get over here. But that function cannot be expressed as just a signed area function. One way you can express that function is as a signed area function plus some vertical shift. And so that's the main takeaway of this video, is that not every antiderivative that you come across in the wild, it's not just a signed area function. Because signed area functions are special antiderivatives that need to have at least one x-intercept. They have that special geometric constraint, but the antiderivatives in general do not need to have such requirements. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.